So the speed is constant, but the velocity is not, because the direction is changing. That's why we say it's accelerating. This is the case where an object is accelerating, but the speed is not changing. Right?
Yes.
And so one of the things that we did is, we eventually developed this later, but if it's accelerating toward the center, and you can calculate that by v squared over r.
Can we use that straight up on that AP test?
It's on the equation sheet.
So anything on the equation, see,
You can just go right
have
to
to
it.
solve, we just throw it on.
That's beautiful.
Those things are big too, so that's like a lot.
Hi, how are you? Good.
Just hanging out with a bunch of high schoolers, nothing better.
Yeah, exactly.
Good.
Give it 4 years, just kidding.
Guys doing okay?
Okay. This has been really good.
So,
Yeah, I know.
Hey.
Could have guessed that from a mile away.
so let's look at the top one. Okay. What does the top equation say?
Vx equals vx0 plus axt.
So it says, look, your velocity in whatever direction can be solved for by taking the initial velocity plus the acceleration times time. I actually write it the other way. I usually
I
do
hate
it.
how they do that.
I know, it's super annoying.
That's such a.
What the?
But do you see that that's the same equation? Now, it says it's giving it to you in the x direction. That doesn't mean it can only be in the x direction. It's in whatever direction you're accelerating.
So it could be in the wall.
Yeah, the next one says the position is equal to the initial position plus the initial velocity times the time plus 1/2 at squared. Right? We just talked about those a minute ago. This next one, it's the v squared equation. If you have to relate these things in kinematics without time, use that one.
19. What is time?
That's a good question.
Don't be reminded of this.
Look, 3 below halfway, okay? 3 below halfway, you're gonna see AC is equal to v squared over r. See it there?
Is that next to it, does that have to do with, what we're learning right now?
It does. I'll pause, I'll do a quick aside. So when we talk about,
Nice.
okay, when we talk about these objects that are rotating, okay, when we talk about these objects that are rotating, so here's the radius, right? Okay? So this is something we drew a little bit ago. We said like, look, the actual physical distance it goes, the delta x, you can find that if you know the angle that you went and the radius, right? Which means if you want to find the linear velocity, you would take the angular velocity times the radius,
Yeah,
right?
that makes sense. Yes.
So two different objects,
Then where's the square come from?
two different objects.
Oh, yeah, where did the square come from?
Okay. Well, this relates to this. I'll show you in a second. Two different objects could have the same angle measure change, right? But they went different distances. So the one on the outside is moving faster because it went more distance in the same time, correct? So if I say, well, this object here is accelerating toward the center because it's going in a circle, that's v squared over r, correct? But if I substitute omega r in for v, I'm going to make a straight up substitution, okay?
Straight up.
You see I just took v and I made a
Yeah.
straight up substitution? V is equal to omega r. And now what we see is we have omega squared r squared all over r, which is omega squared r.
We haven't run that yet. I don't.
No,
We're gonna get to it though?
yeah.
We're gonna be ahead of the curve though.
Well, yeah, you'll just see it.
Imagine how big here right now.
Curve like
Yeah, no, I got it, I'm just.
You are just so funny, aren't you?
Yeah, no, I-
circle.
Forget-
So anyway, that's where that is. Cool? So far, so good?
Keep it in the subject.
Okay.
Oh, why is my camera so dirty?
Do you want a picture of the whole thing?
Yeah.
Oh.
What? I'm trying. We're just doing it together.
Or you can write it down, because writing it down actually
Yeah.
helps you remember.
I'm gonna write it down too.
That's okay.
You know what, Chad?
Chad, the camera's on. They don't mind- Now they don't.
Okay.
You might as well just say.
Were you like me?
Yeah.
Got it. You guys are awesome.
Stop.
When is prom?
20. It's the second, no, it's the first, it's the Saturday. It's the Saturday. I know that for
21st
It's a Saturday.
Yeah.
Man.
We,
I know Lulu's birthday.
I have to be in the
I know
Wisconsin that whole week, but I'm flying back in Saturday morning.
Dude, my boss scheduled in-service for prom.
Ain't gonna happen.
Ain't gonna happen.
Ain't gonna happen.
Sorry.
I'm putting in my time off for everything tomorrow, just like for the summer, so like my coworkers can't say
That's what I
no.
want to do.
I have a whole Sunday, like for like racing and then like vacations and stuff. I'm just like,
Racing, that's it.
All right,
Cargo vroom.
there you got this.
Yeah.
Cargo wear.
Yeah, V6 and season goes crazy.
What you need is the inline four with a turbo one.
Oh yeah, I'm not that, I'm not a big car guy. I just know I want a Hellcat.
Jeez.
Crazy.
You mean a boat? You mean a boat?
What's
What?
the turn, like the turn radius is absolutely disgusting and terrible.
Well, they weigh like 4,500 pounds. Okay, that's actually they weigh like more like 5,000.
Is that like light?
That's a lot.
No,
That's
that's
Really
not.
not for a car.
My
Very,
Civic
very
weighs
heavy.
like 27.
Oh,
I think Susan is like
Our
just
70,
over that.
our 50 years. Yeah, no, those cars are disgustingly heavy.
Yeah. Anyways, sorry.
That's all right. So, the next framework is forces, right? The next framework is forces. So, what we're talking about is the fact that we have some ideas about forces that are important, okay? One of which is Newton's second law.
We're taking a test about Newton's laws, like, actually I haven't memorized them.
Okay.
I don't, actually still don't know them.
We obviously know I don't know them because on one of my tests I wrote acceleration equals force times mass.
That was the best. So, Newton's second law tells you that the acceleration is equal to the unbalanced force.
Oh, we're out of centrifugal, by the way?
Yeah.
Okay.
Well, we're going to return to it in a moment, but we need to do it in the right context.
So can I write a forces section yet or no?
Listen, man, just do what you want. It doesn't matter to me.
Listen,
I don't know.
Okay? So, this is Newton's second law. If you look on the equation sheet, okay, if you look on the equation sheet, it's the fourth one down. It literally says the acceleration is equal to, now, one of the ways the textbooks say it is they use this symbol. What symbol is that?
Sigma.
That's a sigma. And it means to add them all up,
Sigma.
correct?
It's okay.
It means to add them all up. But the thing about this that's important is that these are vectors. So your acceleration is a vector. Your forces are vectors. So when it says add them up, it literally means to add them up as vectors, not as just
So
numbers.
you get net.
So the net is what you get when you add everything up.
It's kind of sick.
Okay? I think the net concept is a little bit easier. I think the unbalanced force is better than the net is good, but this, they call it the sum of the forces. But working with students for a long time, when you say the sum of the forces, if you don't have already a conceptual framework to know that this means add things up and add things up is sum, then kids hear it, and if they don't really understand it, they think it's some of the forces. Not all of the forces, just some of the forces. You see where that could be problematic?
From some interval from 1 to infinity.
Yeah, like you just don't know. You're like, I don't. We're adding some of the forces. I don't know which ones, but some of them. So you can see why I skipped it. Let's just use the net force concept. Now, what does this tell you? It tells you a couple things. What's it tell you about the direction of the net unbalanced force and the direction of the acceleration? They have to be in the same direction, because these are both vectors, and you're dividing by a scalar.
So if they weren't in the same direction, it makes no sense.
It doesn't make any sense at all, because dividing a vector by a scalar just changes the length of the vector. It doesn't change the angle. So the acceleration and unbalanced force have to be in the same direction. They have to be, right? Okay. And it also says these are linear relationships, because this is to the 1 and this is to the 1, which means if you doubled your unbalanced force, you double your acceleration. If you doubled your mass, you'd get half the acceleration. Is that cool? So this is Newton's second law, and it's kind of a big deal. Okay, we're going to use it as our framework moving forward. So anytime you are presented with let's say a force problem, okay? Let's say you're presented with a force problem.
No such thing.
Well, we saw one earlier today, right?
Just pretend that this exists.
If forces weren't a thing, my life would be a lot easier.
Go ahead.
The force of the government.
One.
Now it's not doing it. There.
Oh, that's pretty loud.
This also says, and very importantly, if your acceleration is equal to 0, what does that tell you about all your forces? The force is balanced. The net force is also 0, so your force is balanced. That's really what this whole thing says. See, there are Newton's 3 laws. The first law says if you're an object at rest, your natural tendency is to stay at rest as long as the forces are balanced. That is actually already woven into this statement here. But at the time that Newton made the 3 laws, the church was all up in people's business, and if you made 3 laws that matched like the Trinity, right, the church Trinity, they were a little bit okay with it. So there's really only 2 laws. There's this law, and then we'll talk about the 3rd law in a second.
So Newton's just playing us.
Well, I mean, he was smart enough to realize, like, well, I know the science is good, but I don't want to upset too many people, so let's try to...
It's worth that he killed or exiled.
Yeah. Well, look what happened to Galileo. Galileo had the same idea, right? And they killed him, right? They put him under house arrest and made him drink hemlock. Real problem. Real
Sounds
problem.
like a good way to go.
Just a slight problem.
Yeah. Now, this is the 2nd law. What's the 3rd law?
Oh,
Newton's
inertia.
3rd law, force pins. N3F, I forgot that.
And 3 L, like that, I think where you should do
Yeah, yeah.
What does it mean?
it.
Forces have to come in pairs with equal and opposite something.
The reaction statement.
So the action-reaction statement is a little problematic because it implies a time difference,
That there's
a cause and effect. But these are simultaneous force pairs.
Did he write it like that, or is that something that was just devised after?
So I don't know, because I don't know what the original writing looks like, but what we understand now is that
Yeah, exactly.
these force pairs occur simultaneously in the opposite direction with the exact same magnitude force. There's nothing you can do about it. It's the law of the universe. So we see it manifest like this. So this truck is going to smash into this car. The truck is bigger, it's moving faster, it's going to smash right into it. Which is going to apply a larger force?
The truck. Oh, no. Both. Same, equal forces. What am I saying? How dare I?
No, but this is the moment though, where you're reconciling
Understanding.
your own personal concept with the actual science concept. right? The forces they exert on each other have to be the same. You can't get away from that. They have to be the same.
That's why punching somebody hurts.
Literally, it's exactly why punching somebody hurts. Okay? Because no matter, the harder you hit them,
The harder their face hits here.
exactamundo. So the force of the truck on the car is equal to the force of the car on the truck. Right? But the truck pushes the car to the right. Which way does the car push the truck? To the left. So one of these is negative.
Yeah.
So we'll make that one negative. But is the resulting motion the same?
Maybe.
No.
Definitely not.
Oh, no, because they're gonna,
Well, the truck is gonna hit and slow down and keep moving forward.
the car's gonna go flying.
The car's gonna go flying forward. Why does the car have a larger change in the speed than the truck does?
Does that have to do with inertia?
It is absolutely because of the mass, it's because of the inertia.